Okay. Hi, everyone. Thank you for
Awesome.
coming to this talk. This talk is being done by Xingyu Li from the University of Toronto, Mississauga, and it's called A Magic Trick Using the Set Deck. Go ahead.
Okay, great. So thank you everyone for joining me today. And a quick introduction about myself. I'm entering my third year at the University of Toronto, Mississauga. I am studying mathematics specialist. And today we're gonna dive into the world of recreational mathematics and how we can use the set deck to create a very interesting magic trick. This trick is originally inspired by Persi, Diaconis, and Ronald Graham in their book. And the original trick is called TetraCycles. It is actually done with a normal a deck of cards. However, it is being minimized to 32 cards, I believe, due to some constraints. However, we managed to use it on the set deck. So for the structure of this talk, okay, cool. I will first talk about what the set is for those that haven't played the game yet. And then I will demonstrate this trick from an online perspective. It will not be the trick that I will be performing offline, but it will be the best I can do given the virtual circumstances. And then I will talk about the math behind it, specifically something called the green sequence and how this applies in this trick. And then I'll talk about the graph theory behind it, which is essentially how we generate this kind of sequence. And finally, I will talk about the offline version, which is much more amazing and how it is being done by the magician. Okay. So what is the game of set? For a set, the deck consists of 81 unique cards, and each card varies in 4 features across 3 possibilities for each. They are number, color, filling, and shape. And as you can see, for each feature, you have 3 choices. So in all, if you need all unique cards, that will be 3 to the power of 4, which happens to be 81. So the following are examples of some random cards in the deck. So as you can see, the first one would be, the number will be 2, so it has 2 shapes. It has a purple color, and the filling will be striped, and the shape will be oval, and vice versa for the rest of them. So I will do a quick demonstration of this trick from an online alternative version of it, actually. So this is a pre-arranged deck from left to right and then up and down. So I would like an audience member to pick one feature. So you could pick number, color, filling, or shape. So just type it in the chat. I have to go back here. Color. Okay, cool. And now I need 4 people to type in one choice each. So for example, if you want to participate, you can type in purple, you can type in red, and you can type in green. And I need 4 of them. Okay, we have green. Okay, that's green, green, purple, purple, red. Okay, that's 1 too much. So I'm just gonna pick green, green, purple, purple, and for this trick. So as it turns out, the sequence that you just typed, which is completely random, is already embedded in this deck. So let's see if we can find green, green, purple, purple here. So we need 2 cards that have green colors following 2 cards with purple colors. If anyone find it before me, just, okay, I found it. So it's here, green, green, purple, purple. And as it turns out, no matter which feature you choose and which 4 possibility you pick, it will always be embedded in this deck, which is kind of weird because that seems like a lot of possibilities. So now I will talk about how this is being done using something called a degree sequence. The definition of a degree sequence is actually a cyclic sequence of a given alphabet A with sides k, and for which every possible subsequence of length n in the alphabet appears as a sequence of consecutive characters exactly once. We denote a degree sequence as bkn. So k represents the size of our alphabet, and n represents the order of each subsequence. So I will give an example here. So this is a subsequence of this is a degree sequence of B33, and we will use the alphabet 0, 1, 2 arbitrarily. And as you can see, we have a sequence here. And you can check that each of the 27 strings of length 3 from the alphabet 0, 1, 2 appears exactly once as a subsequence. So for example, 0, 0, 0, you can find it here, 0, 0, 1, 0, 0, 2, and vice versa for all of them. A special one would be 2, 2, 0, because remember this sequence is cyclic. So technically there's no start and end for the sequence. It's almost like it's going around like a circle. So you can find 2, 2, 0 by wrapping it around, and you can find 2, 0, 2 by wrapping it around as well. So that is an example of a different sequence. And now the question is, how do we find those sequences? Like, I'm sure that maybe for something like B22, we can just brute force it and just keep guessing it. But as you can see for B33, it's already kind of hard to just like brute forcing it and trying it out. So there has to be a way for us to find these kind of different sequences. And that's called a different graphs. So essentially, this also proved the existence of different sequence. So the definition of different graph is a bit long, but I will go over it in a very detailed way. So a different graph, we're going to denote them as GKN. This is not an official notation. I used it so that it doesn't mess up with the BKN definition of a sequence. So this is a directed graph with k to the power of n minus 1 vertices. So that's the number of vertices. And each vertices is labeled with all possible strings of length n minus 1 from the alphabet. So for each vertex, we're going to label them as this from A1 to n minus 1. And each element, D from the alphabet. And there's a directed edge from V to the vertex labeled A2, n minus 1, D. So if you compare these two vertex, this one and this one, you can see the changes is that the A1 here is being removed, and we are adding a D to the end of it. And it's almost like it's shifting by one bit, by one digit, using this direct edge called D. So essentially, this is being explained here. We have an edge labeled D from vertex V, which is this one, to vertex W. If the label on W can be obtained by appending D to the label on vertex V, with the first character removed. So I will give an example here. So this is a different graph of G33, like the different sequence we just talked about. So as you can see, it's very interesting that we can actually come up with a symmetric graph of it. And these are the vertex. Those are all the possibilities that you can construct a length 2 using 0, 1, and 2. So we have 0, 0, 0, 1, and so on. So let's look at one example here. For example, from 2, 1 to 1, 2. So I have a direct edge here, labeled as 2. And why is that? Well, because I can append this 2 to the end of this sequence and remove the first digit here and obtain 1, 2. So it's the same thing for all of them. This is essentially how this graph is being constructed. So we construct the vertices first, and then we connect all the possible edges. Essentially, it's like transitions from one vertex to another. And as you can see, 1, 1, 2, 2, and 0, 0, it loops around itself because, well, you can add a 0 to the end and remove another 0 at the beginning, and you still get 0, 0. Okay. So given this graph, how do we get a different sequence out of it? Well, to get that, we have to first introduce the idea of Eulerian circuit. And it is also called a cycle. It is actually a trial in a finite graph that visits every edge exactly once and starts and ends on the same vertex. Notice that here we're talking about edges, not vertex. So traversing through the Eulerian circuit actually gave us a different sequence. So that's quite fascinating how this is being done. So I will give an example here. So one Eulerian circuit here in G33 is given by this sequence. So let's say we start with 2, 2, and we go to 2, 0. So by completing this sequence here, we can pass through every single edges in the G33 graph. And then after that's being done, all we have to do is that we read off the edges, the label on the edges. And by doing that, we actually obtain the different sequence that we had before. So now I'm going to talk about a special different sequence for this trick in particular. So we've been dealing with an alphabet 0, 1, 2. And now in order to apply it to a magic trick like set, we have to give context to it. So we can interpret each set deck as a string of length 4 over the alphabet A. And the reason is that a set deck can be described by 4 features, and we can just give a random number to each feature. Sorry, not random, we're giving context in this table here. So the following table provides a mapping between the strings and the set deck. So for instance, the string 0000 will refer to the car, so we just go to the table. It will refer to the car with 3 shapes: purple color, striped, and diamond. So that's how we're matching every single 4-string sequence to a set deck. Sorry, to a set card. So using this encoding, any de Bruijn sequence with the form B34. So notice that 3 here is still the alphabet, 0, 1, 2. But 4 here is the length of the substring. And remember that we need 4 numbers to describe each set card, which is why it's 4 here. It allows us to read off cyclically all 81 consecutive subsequences from left to right. It's producing an order of the deck necessary to perform a trick. And based on this construction, every 4 consecutive digits of the sequence provide full information for 1 card and partial information for the 3 cards after it. Because in order to describe the 3 cards after it, we also need some of these digits, but not all of it. So the question is, do we have to memorize the entire sequence of length 81? Well, just imagine you're performing this trick in front of 100 audience, and you just sitting there or standing there, and then you're just trying to memorize the entire sequence for like an hour. That's not a good magic trick to do. And luckily, the answer is no. And how do we do that? Well, as it turns out, there are actually some de Bruijn sequences with very nice algebraic properties. It gives us the ability to predict the sequence beyond a given substring in order to perform the trick without needing to memorize all the terms of the sequence at all. So this is our definition of this, actually a recursive de Bruijn sequence. And we define the sequence by starting off with 0001. And then for the rest of the digits, it can be automatically generated by using this recursive definition. So each Bn represents a digit at the position n. It's obtained by adding Bn-3 plus Bn-4 in modulo 3. And thus, given any consecutive substring of the form Bn, Bn plus 1, n plus 2, and n plus 3, the next entry, Bn plus 4, is actually the remainder of the sum Bn plus Bn plus 1 when divided by 3. So actually using this definition, we can generate a recursive sequence that happen to be de Bruijn. And when I first got introduced to this idea, it's quite fascinating because having a de Bruijn sequence seems to be a very strict condition, but somehow we can have a recursive definition of it. And what's even more amazing is that for B34, actually the total number of de Bruijn sequence possible is 1.26 times 10 to the power of 19. That's a huge number, and you can actually find that equation on Wikipedia, and I believe there's a proof of that. However, there are only 8 of them with a recursive structure. So 8 out of 1.26 times 10 to the power of 19 has this kind of property. And that just seems really fascinating to me. So this is how we generate a sequence, like the definition before. So we start off with 0001, and then we can generate each digit by adding it up. So the 5th digit will be 0, the 6th will be 0 as well, and the 7th will be 0 plus 1, mod 3 is 1. So by continuing this process, we end up with the complete de Bruijn sequence of length 81. And this is the sequence that we're going to use for the trick that we call in TetraCycles. Again, it's inspired by in cycles, but tetra means 4 because we have 4 features here. Okay, so now it's time to, I guess, reveal the in-person version of this trick. So preparation, sorry, just let me move this a bit. Okay, great. So to prepare for this trick, we need to arrange the deck in the specific order based on our de Bruijn sequence. So our first card will be 0001, second one will be 0010, third one will be 0100, vice versa. And by going through the entire de Bruijn sequence, we arrange the entire deck. Great. And now we are in the performance stage. So as the magician, you are allowed to cut the deck repeatedly. And the reason is that it's cyclic. So the property of the burn sequence remains no matter how you cut the deck, but don't shuffle it. If you shuffle it, the sequence, the property is gone, but cutting is fine. And this has actually been done in a lot of those kind of mathematical magic trick because a lot of sequences behind it, it's cyclic. So now the magician hands out 4 consecutive cards to 4 volunteers, kind of like what I did before in the virtual version. And then we can ask, which feature would you like to describe? And let's assume the volunteers choose shape. And now the magician asks, would all of you holding the diamond, please raise your hand. So let us assume that the third person raise your hand. So we know that, okay, he or she has a diamond. And now we ask, would everyone with an oval please raise your hand? So let's assume that first and the fourth person raise their hand. Cool. So after all that, the magician correctly named all 4 cards in order, including their numbers, colors, shadings, and shape. So as you can imagine as an audience, this is quite astonishing because from an audience perspective, all you know is some partial information about one feature, but somehow you can name all the features of them and you can name the 4 cards exactly as it is. So we will describe this again from the magician's perspective. So here's a quick graph showing what is going on, just to have a better visualization of it. So if the third volunteers has diamond and the first and the fourth volunteers has oval, then we automatically know that the second volunteers must have squiggle because we only have 3 possibilities in total. And now we have obtained the order: oval, squiggle, diamond, and oval. And if we match it to the table, that actually correspond to 1, 2, 0, 1. So that's the sequence we have right now. And we notice that shape is our last feature in our table. And to know the complete information of all 4 cards, we actually need to go backwards. Well, if you're performing this trick, you would wish that the audience pick number because that way it's really easy. And then you can just go forward by doing the modulo 3 addition. However, if they pick shape, it's kind of tricky because you have to think backwards, but it's actually not that bad. We just need to deduct the 3 digits before 1201. And if we do that, we know the full information of the 4 cards because the first card will be just BI to 1, and then the second BI plus 1 to 2, and vice versa. So remember that we always need 7 digits to complete this trick. Okay, so by our recursive definition, but in reverse, so instead of adding right now, we're doing subtraction. So in order to get the BI plus 2 digits, we're doing BI plus 6 minus BI plus 3. So 1 minus 1, we get 0, and mod 3, that's still 0. And we'll do the same thing for the rest of them. And BI plus 1 will be 0, and BI is equal to 2. So that in that way, we have obtained the entire 7 subsequence of the form 2001201. And in this case, at this point, we can read off the algebraic representation of each card in order. So if we have 2001201, what's going to be the 4 cards? Well, the first card is going to be 2001. The second will be 0012. The third will be 0120, and the fourth will be 1201. So again, we need to use the table. So the only thing you have to kind of remember is the table and how the numbers being matched to each feature. So by applying the table and match each number with its corresponding properties, we obtain the 4 cards on the left and complete the trick. So by that point, we know exactly what cards these 4 volunteers are holding. And we can do some like magical things that magicians do, like trying to read your mind, stuff like that, and then be like, okay, this is the card you have. So that's how we complete the trick. And at the end, I would like to, again, talk about how it all started. This is a variation on the TetraCycles trick developed by Persi, Diaconis, and Ronald Graham, elaborated in their book, Magical Mathematics. And reading chapter 3 on universal cycles actually got us started on this exploration. And we would like to dedicate this work to the mathematical legacy of Dr. Ronald Graham. And there are three of the very influential mathematicians in the recreational mathematics, and both John Conway and Ron Graham passed away this year, which is a huge loss for the entire community. So I hope that my work somehow has a bit of a effect on this community. And I would also like to thank Professor Park Nayedi at the University of Toronto, Mississauga for supervising the summer research, as well as Dr. Com Agar, who is editor of Mathematical Associates America. He has been given constant input to this research, and he is actually the one that made the beautiful de Bruijn graphs. A bit of a fun fact about the de Bruijn graph is that for the G33 graph, there's actually a planar version of the graph. So if anyone's interested, I can actually send them that version. I didn't include that because I feel like the symmetric one better fits with the slides, and it seems very magical. Then there's a symmetric version of it. And that's everything for my talk. How am I doing on the time?
You're doing great. Yeah, there are about 4 minutes left, so we can definitely take a couple questions.
Awesome. Okay, let me read the chat. Sorry, I haven't been reading the chat because it's on full screen. Okay. Yeah, right. What is a cyclic sequence? So a sequence is cyclic, meaning that there's no beginning and the end. So imagine a normal sequence has a beginning and the end, like a line. A cyclic sequence wraps around, so almost like a circle, right? So there's no beginning, there's no end. So does that make sense? I hope I'm explaining this like intuitively. Have you considered looking at recursive de Bruijn sets with other alphabets? We haven't, but we talked with Tom Agar, which is the editor, and he thinks that this whole de Bruijn sets could be an entire industry because it's contains so many properties that can be applied to, like, not even magic tricks and other things as well. And fun fact is that the de Bruijn sequence is actually very well applied in cryptography, because imagine if you have passwords, right? And you have a sequence that contains every single possibility that this password is being written. So that's a very much more efficient way than just doing all the permutation and stuff. How many places in the de Bruijn cycles is there an actual set of consecutive cards? How many places in de Bruijn cycles is there an actual set? Sorry, I'm not sure what that meant. Do you mind explaining that? Like the cards are embedded in the sequence everywhere. Okay, 3 cards were right. So sorry that I forgot to mention that. So in this talk, I didn't talk about actually how to play the game. And as it turns out, that also contains some very interesting algebraic properties. So 3 cards were each. Exactly. So the way you win the game is, sorry, not win, the way that a set works is that for each feature, it's either all the same or all different. And you can actually look at that from an algebraic perspective. And you can, there's a lot of theorems behind it, like the probability of having a set within 12 cards and everything. So there's a lot of interest reading on that, and you can find them online as well. Yeah. Is there any other questions?
Okay, if we don't have any other questions, if anyone has one, if they want to stop me real quick, say like I have a question. No, okay. If we don't have any more, then yeah, thank you so much for your talk. Thank you so much everyone for attending.